All right, today we're putting two really powerful laser technologies under the microscope. We're going to have them go head-to-head in a battle for supremacy in the tiny world of micromanufacturing.
So, ever wonder how they do it? How do you drill a hole that's thinner than a single human hair into the advanced electronics that are literally all around us? I mean, the phone in your hand, the computer on your desk, they're packed with components so small it's kind of hard to wrap your head around. And building them, that takes tools with unbelievable precision.
And that right there, that's the big challenge. As our tech gets smaller and faster and more powerful, the tools we use to build it all have to keep up. We have to work on a scale that's almost invisible, and that's exactly where our story kicks off. Okay, so let's meet our test subject. This is beryllium copper, but it's coated with these super thin layers of nickel and gold. This stuff is a real workhorse in high-performance electronics. Why? Well, that special coating helps with electrical performance and stops corrosion. It's also really tricky to work with.
So to drill a microscopic hole into this tough material, two contenders are stepping into the ring. And listen, this isn't just some lab experiment. This is a proper showdown to see which technology is really the right tool for this incredibly demanding job. In one corner, we've got the infrared laser, or IR for short. You can think of this one as the industry workhorse. It's powerful, it's everywhere, and it's pretty affordable. And in the other corner, the ultraviolet, or UV laser. Now this one's the specialist. It's more expensive, for sure, but it's famous for its incredible precision. So it's the reliable old champ versus the pricey new challenger.
Now you can't have a fair fight without some ground rules, right? So the experiment has some really strict rules of engagement. This is all to make sure we're comparing the lasers themselves, not just, the settings they happen to be on.
So here's the game plan. The target, of course, is our coated beryllium copper. The power for both lasers, locked in at 20 watts. The one thing we're going to change is the speed, or what scientists call the repetition rate. We'll test it at a slower speed and a faster one. And the goal? It's simple. Who drills the cleaner, more precise hole? Let's find out.
All right, so after firing both lasers under these exact conditions, the results were in. And honestly, they were surprisingly clear. There was a definite winner. First up, the IR laser. The big takeaway here is just how inconsistent it was. At the slower speed, it blasted a 53-micron crater. But when they sped it up, the crater actually shrank to 33 microns. So the results were all over the place depending on the settings, which is not what you want for precision work. And this quote from the study, man, it just says it all. The researchers found that the IR laser left behind a rough edge, full of all this melted and resolidified gunk. I mean, it got the job done, but it was messy. It was basically brute force. Okay, now let's look at the UV laser. And wow, what a difference. We're talking rock-solid consistency. It didn't matter if it was firing slower or faster, the crater size stayed right around 25 microns. This is the kind of reliable, repeatable result you need for micromanufacturing. And the quality totally backs it up. The study found the UV laser left a comparatively neat edge. No mess, no fuss, just clean, precise material removal. The difference is just night and day. And that kind of precision is what lets engineers design smaller, denser, more reliable electronics.
So we have a clear winner on performance. But the big question is, why? Well, the answer is in the fundamental physics of how light interacts with stuff. Let's dive into the science of absorption. This is really the heart of it. Why did one laser act like a surgical tool while the other one was more like a blunt instrument? Well, it all comes down to one absolutely critical factor. And that factor is absorption. For the UV laser, get this, over 70% of its energy was directly absorbed by the beryllium copper. That energy went straight into vaporizing the material, cleanly and efficiently. Now, compare that to the IR laser. Are you ready? Only about 5% of its energy was actually absorbed. So, where did the other 95% go? Well, it basically splashed off, creating a ton of extra heat that just melted the area around the hole, causing that messy crater we saw. So here's the bottom line. It's all about the absorption rate. It's the difference between a surgical scalpel and a thermal sledgehammer. The UV laser's energy is used with incredible efficiency to cut, while most of the IR laser's energy is just wasted as damaging heat. And understanding this has some huge implications. It tells us that for the next generation of tech, we can't just pick the most powerful tool. We have to pick the smartest one. So let's just quickly recap the big takeaways. First, the UV laser is way cleaner and way more consistent for this job. And the reason why is that crazy high absorption rate, over 70% compared to just 5% for the IR laser. This efficiency means way less heat damage and mess, making it the clear choice for building the complex, reliable electronics we all depend on.
You know, at the end of the day, this isn't just a story about two lasers. It's about understanding the fundamental physics at play. And that knowledge, that's exactly what's going to let us build the smaller, faster, and more powerful technology of the future.
Which kind of leaves us with one last big thought. We've gone from mechanical tools to these incredible laser scalpels. But as we keep pushing smaller and smaller down into the nanoscale, what's next? What kind of entirely new tools are we going to need to invent to keep building our amazing technological future?